this idea that we can add up infinitely many times and it can go to a number is so mind-boggling. Let's see one more example like that. All right, so we have an infinite series, which is 0.1, 0.01, 0.001, and so on. All right, before I go any further, let's note the explicit sequence that was building this. So there was a sequence that has an explicit formula. I'll call it A sub n, right? And that sequence, and you can see, right, if this is A sub 1, this is A sub 2, this is A sub 3, A sub 4, 1 went to a tenth, a hundredth, a thousandth, 10,000th. So we're obviously taking 1 over 10 to the n power. Very similar to the previous problem, where it was 1 over 2 to the n power. Or if you like, you can say it's 0.1 to the n power. That would also work. That's the sequence that's building this series. So sequence is the individual numbers. The series is when you add them up. All right. So for part 1, they just want us to add them. Right? That's it. That's all they want us to do. So that's no problem. We can add. All right. So S1 is the first one, which is 0.1. S2 would be adding the first 2, which is 0.1 plus 0.01, which would be 0.11, rather obviously. All right, so there's this one, there's this one. S3 is adding the first 3, which is 0.111. S4 is adding the first 4, which is 0.1111. All right, so not much there. That's fine, right? So we got part A done. All right, now for part B, here's where the fun begins. They want us to find a value that we would assign to the infinite series. And to do that, I kind of want us to think about this a little bit more. So if I take the sum of that sequence from 1 to infinity, right? That is the sum from 1 to infinity of 1 over 10 to the n. Or if you like 0.1 to the n, whatever, you know, it's all good. All right, so then that would be equal to, and technically you could write it as 1/10 to the n. Here, I'll even blow your mind a little bit. Here, you could go like this, right? Because 1 to the n is just 1 to the n, right? It doesn't make any difference. And 10 to the n, right, is 10 to the n. So that's another way to write it. I can even write it up here. 1 over 10 all to the n power. That'll work. All right, so that is equal to whatever this infinite sum would be. It's equal to the limit as n goes to infinity of our partial sum sequence, which is right here, right? The partial sum is these values right here. Okay, so what is that partial sum? Where are we going to? Well, we just keep adding on 0.1, 0.11, 0.111, 0.1111, right? So that would be equal to, where is this going to? Well, it's going to 0.1 with a bar on its head, right? It's heading to 0.1 to the infinity. So what is that, right? So that's fine. I mean, that's perfectly acceptable answer. But do you know what that is in a fraction? It's 1/9. Here, allow me to show you. I don't know if anybody ever taught this to you in school somewhere along the way. So let me make this part disappear. Let me just kind of put 0.1 divided by 9 is 0.111 repeating. I don't know if you knew that. So keep in mind what that means. That means that 2 divided by 9, 2 divided by 9 would be twice that. So this is example 9 right here. So keep in mind, just a little note, it didn't ask us for this. It'd be that, right? 0.222 repeating. So when you see a repeating decimal like that, where it's the same number over and over and over, that actually is a math topic that you learn usually in like pre-algebra somewhere along the way. So note there's a little trick to this that we might want for later use. 0.2 repeating is 2/9. 0.7 repeating would be 7/9, etc. It's a little math trick. It's actually an arithmetic trick, right? So it's just a little note. So we've answered the question. That's the value we would assign the infinite series. The infinite series is 1/9, right? Or 0.1 repeating. That's the infinite series. And these were each of the values for part A. So think about what we're saying. If you have a sequence, A sub 1 through A sub k or whatever, going on forever, and you sum them, this guy right here is called an infinite series. So this piece is called an infinite series. You're adding up to forever. All right, now the sequence of partial sums is a portion of that. The sequence of partial sums is the sequence that's built from adding up pieces of this. So you're going to add up the first one, then the first two, then the first three, then the first four, right? And you keep adding and adding and adding, and you get to the first n, right? So it's a finite system because you're adding up only the n. But those partial sums have a limit, and that limit would mean that it's convergent. So if you get a number L, if it has a limit L, then we say it converges. Like this one above converges. I can add that. This is convergent. Right? Because it converged to 0.1 repeating. Right? If it converges to a specific value, wonderful. Right? And then this piece, this sequence, is your partial sums. Oops, sorry. Right there, green. Right there. That piece, when you stop at n, that's your partial sum, n. So you're taking little sub-bits of that infinite series, right? Because you can't handle infinity, but what you can handle is little piece, little piece, little piece, partial sum. Add it up to 1, add it up to 2, add it up to 3, and you've built a new sequence out of those values. And then what you're doing is taking the limit of that new sequence. If the limit of that new sequence is a number, it's convergent. Otherwise, we say it diverges if there is no limit, right? All right, let's look at another example for the sequence of partial sums. We want to find the sum of the first 1, 2, 3, and 4 terms of the series. Okay, so we're going to be building a partial sum sequence here. So for letter A, so it wants us to start at 1. So S sub 1 would be equal to 1 over 1 times 1 plus 1, which is 1 over 1 times 2, which is 1 over 2, or 0.5, if you want to see it as a decimal. S sub 2 would be adding up. So you're going to take the half that we already have plus another 1 over 2 times 3, so that's 6. So that's 1 over, so a half plus a 6, which is 2/3, which is 0.6 repeating. Then S sub 3 would be the half plus a 6 that was before, plus then we would take 1 over, well, it'd be 3 times 4, which is 12, which is 3/4, or 0.75. And S sub 4 would be a half plus a 6th plus a 12th, and then 4 times 5 is 20, which is 4/5, or 0.8. And if you don't believe me, I can show you in Desmos. There we have it. So I have those sequence values here, a half, a 6th, a 12th, a 20th, which is 0.05. I don't really need the 5 and the 6. I can make those go away because it only wanted the first 4. So I can just kind of delete those. All right, so you can see these values, and sure enough, the fractions I'm saying, which are 2/3, 3/4, and 4/5, they're actually correct. I didn't even bother with the half. So there's a new relationship going on, right? And it's, let's think. We take our first number and it goes to 1/2. So it's n over, n8, sorry, I'm defining this as n8 over n8 plus 1. And then let me see, if I put 1 in, it gets me a half. If I put 2 in, there it is, that's 2/3. 3 in, that's 3/4. 4 in, that's 4/5. I have a new relationship, which I'm seeing between those sums. And that creates a new sequence in and of itself. And that's actually part B, I believe, that's being asked for. So I've got these new figures right here. So it asks for this number, this number, this number. Technically, either the fractions or the decimals will do, but it's easier to figure out the formula when you're looking at the fraction, because you can see that it's 1 over 2, 2 over 3, 3 over 4, 4 over 5. There's a pattern here which is n divided by n plus 1. Right? So 4 over the next number 5, 3 over the next number 4, and so on. So that's part A and part B. And then it's not really part C, but I'll call it part C. It wants us to make a conjecture about where this is going. Well, we don't really even have to make a conjecture. I mean, we can. This is still a conjecture even when I go do this, but let me grab another number. 5, 6, 7. Let me try 10. Let me try 100. Let me try 1,000. Where are we going? We're going to 1, right? You can see these values are getting closer and closer and closer to 1. And sure enough, that's where we're going. That's my conjecture. I can't prove it quite yet, but my conjecture is the limit as n goes to infinity of my sequence. Actually, let me write it this way. Here. Give me 1 second. All right, my conjecture is that if I take this series from 1 to infinity of 1 over k times k plus 1, that is equal to the limit as n goes to infinity of s sub n. Right? That's my conjecture, right? Oh, and I guess I played fast and loose with my subscripts. I'm sorry. I can make this k. You can make it k in Desmos as well, actually. Desmos doesn't care if you use n or k. So I'll make this k just to make it so it's the same letter both times. There we go. Which my conjecture, from looking at Desmos and thinking about it and seeing these problems, seems like it's going to 1. This guy right here is s sub n. Oh, I guess I could do it this way. That's s sub n. That, or s sub k, I should say. And this is a sub k. Sorry, some books use n a lot, some books use k a lot, lowercase k. It does not matter. They both work as index values, so whichever way you like. Just keep it consistent. So if the problem gives you k, use k. If the problem gives you n, use n. It's good either way. All right, so that leads us to just some definitions real quickly before we're done. So remember that the sequence is the list of numbers, right? So sequence is your list of numbers. You can define it explicitly right here. Right? That's an explicit relation. Or you can define it with recursive or recurrence relation, which is an implicit relationship. As you can kind of tell, explicit is going to be more useful for us in the long run. So that's what we have. All right, so then an infinite series is when you're summing that sequence to forever, right? So you go up to forever, and that's what makes it infinite. Finite actually has a number up there, right? Infinite will have infinity. Now, the sequence of partial sums is this new sequence that's built from adding up pieces of that series. And we use that to evaluate this series right here. So we took the sequence of partial sums, which we developed right there, right? The sequence of partial sums is right there. And we used it to define what that series must be, right? We took the limit of that sequence in order to come up with what the sum must be. I hit my camera. And then last but not least, don't forget where this is all coming from. This is discrete, right? When we look at sequences and series, we're looking at dots, right, on the graph, as opposed to functions, which are continuous. There is a relationship between them, but we'll deal with that in chapter 11. For right now, we're going to be working with sequences, discrete values that you'll be adding up, right? This is a whole new world, right? And just keep in mind, we could use k. This would be a sub k, right? That happens a lot. And we'll use the integers or the whole numbers. So sometimes they'll use the whole numbers, sometimes they'll use the integers. So it either can start at 1 or it can start at 0. Oh, sorry, the natural numbers. Natural numbers or integers or whole numbers. So sometimes they'll let you go negative. It's possible. Natural numbers, whole numbers, those are the most common ones, the natural and the whole. And remember, if it's finite, it will have a number up here. It will stop at a particular value. If it's infinite, it will go to infinity.